Hey.
Just badgering myself.
I'm sorry?
I finished beating myself up.
Okay. Did you finish?
Yeah.
Huh?
Yeah.
Not going to come back?
Well, when can I come back? During, of course, one of your office hours.
Yeah. Okay, let me pause this a moment so I'm not recording it. Okay. Why did it do that? All right, sorry about that. I was getting ready to record, and a student came in. I thought it was one of you, so I stopped, and then she had questions from another class, so I just now getting around to recording. She was doing a makeup test and couldn't make up her mind whether she was going to come back or not, or when, or that kind of stuff. So sorry we're late getting started. I've been trying to. Last week I requested a vehicle to go to the meeting I'm required to go to in Mobile next week. They said they'd take care of it. And then this week I checked twice and they still hadn't heard anything. And finally today I checked. I've called 3-4 times, and the person in the vehicle office emailed once, and finally I got in touch with somebody, and they said, "Oh yeah, I thought I sent it, but now they're going to send it again." So I've been trying to trace down the vehicle. I only have 30 minutes from this class to the next class to pick up the vehicle because I'll be in class until 5:45, and their office is closed after that. So I've got to. I just between a rock and a hard place. So I finally got in touch with somebody. So hopefully I'll have a vehicle with me at the end of this class. So anyway, let's get going with today's class. I'll wait and do announcements until some people come in, because I don't want to make announcements and nobody ever hear them, so I'll wait till someone comes in. Now, I was trying to see where we left off last time, and I have a feeling that I didn't mark the page correctly. I know that we did, I have it marked 68, but we did 68 last time, page 68. We did example 7. I guess that's what we were working on. We were working on example 7, and I think we had messed up a number in it, so that's where we ran out. So we're picking up now, I think, in 210, though I thought we did this one as well. We did. I'm pretty sure. I remember that proof. So I'm thinking now, oh, yeah, we're at systems of equation. I put my thing in the wrong page. Top of page 70. All right. For square systems, now what do we mean by square systems? Now we're talking about systems of equation. Square systems, that means same number of equations as you have unknowns. That's what they mean by square. If you're doing the Gauss-Jordan or Gauss elimination, it's not a square matrix because you have the adjoin the solution column to the matrix. But for the square system, that means same number of variables as you have unknowns. Okay? That's the same thing. Same number of equations as you have variables or unknowns. Okay. Now, this following theorem to determine whether the system has a unique solution. Okay? So, the deal here is, starts like most of these others started, A is an invertible matrix. Now, to be invertible, you know it has to be square. Just because it's square doesn't mean it's invertible necessarily, but if it's invertible, it's got to be square. Okay? And it has an inverse, obviously. Then the system of equations AX plus B, AX, X being the variable vector, is equal to B, where B is your solution vector, has a unique solution provided that, or given that solution will be x, solving for x, the vector x is equal to the inverse of A times B, vector B. Okay? If A is invertible, then any square system of equations, same number of variables as equations, will have a unique solution, and that unique solution will be this. All right, we finally have a student. Okay. So let me get caught up.
Always first, never last.
What's that?
Always first, never last.
All right. He says as he comes in, how many minutes late? Okay. All right. Terrell is here, so I'm glad you're here. Okay. Let me first turn on the projector and turn on the light for you. And then I will make a few announcements. I don't like to make announcements to an empty room because I'm not sure anyone will ever hear, but just in case you need to know this tomorrow, or what's that? Okay. Now, I'm pretty sure I said this last time, that they usually ask for midterm progress reports sometime after midterm, which we're now after midterm. Now, I haven't seen my emails today, so I don't know if they asked for it today, but I scanned them very quickly yesterday. I may have missed them, but I didn't see it on there yesterday. So they haven't asked for it yet, but at some point they usually ask for midterm progress reports, which means we tell them what students have D's or F's at midterm. Now, unfortunately in this, one of my best classes ever, of course, I have one research paper, one, only one, and only one test one that's been turned in so far. Okay.
It's 2 research papers.
2 research papers. Okay, we just doubled our number of research papers.
And on the test, I have it to you as soon as possible.
Do what again?
The test, I have it to you as soon as possible.
Okay, yeah, well, that's all right. I have a score for you. That's the important thing. That means 3 people out of the 7 may be passing at midterm. I hate to have 4 out of 7 failing at midterm, but hopefully I'll get some more things in early next week. Now, why do I say early next week? I'm not going to be on campus tomorrow at all, either campus, okay? The reason is I've got to make a trip to Mobile for the college. It's official business. A meeting starting down there, I found out yesterday they're starting at 11:30 rather than 12, so that means I have to leave even earlier. So I'm planning to leave the house before 7 in the morning, and I'll drive 4 to 5 hours to get there, have a meeting for 3.5 hours, and then get in my car, the vehicle, and drive back here for another 4 to 5 hours. So it'll be probably after 8 o'clock before I get home tomorrow night. So from before 7 in the morning until probably after 8, that's better than a 13-hour day for a 3 to 3.5 hour meeting. Okay. That sounds pretty efficient, doesn't it? Okay, so anyway, I've got to do now. How that impacts us a little bit, right at 12:45, when this class is over, I've got to leave and go over to pick up the vehicle, or the book for the vehicle, because I submitted the paperwork last week, and I was told, yes, we'll take care of it, and stuff. I usually like to carry the paperwork and make sure it gets in the right hand. But Dr. Crawford didn't seem to be in the office, and the secretary was on her cell phone, and she said, I'll take care of it. I said, okay. And she said, no, it's fine, man. So anyway, I checked earlier this week, no news, okay? I checked again, no news. Okay, now they did say the email had been down part of the week, and they're afraid maybe she sent it when the email was down, but she should have been able to pick up on that. Evidently not. So I checked this morning, no. I called her office, Dr. Crawford's office, left messages at both, and then I called back in between the last 2 classes, and no news either place. So I called her office again, left another message, called Dr. Crawford's office, and she picked up. I said, Leanne hasn't received it yet. So, oh, I thought I said that. Yeah, well, let me check on. Yeah, I'll get it taken care of, like I've been told before. So, I don't know if there's a vehicle or not. So, I've got to go at 12:45 because at 1:15 I start a second mini term class. It goes until 5:45 tonight, and the office over there closes it between 4 and 5. So there's no way I'm going to get the car unless I get it between these two classes. That's my half-hour lunch hour. Okay, so that's the only time I have. I was going to get it this morning. I came in early. It wasn't. They hadn't gotten paperwork. Okay, so anyway, that's my sad talk. Okay, now the other issue is next Friday. I also have an eye appointment, but it's right across the road from here. So I'll be on this campus just a little bit before 8, but the appointment's at 8:15, so I got to head right over there. And then after that, I'll try to go to the Birmingham West campus where I usually go on Fridays. If I don't feel like I can drive safely, I may work here for an hour or so and then go over there, but I think I'll be able to drive. Usually you can after they mess with your eyes, but usually it's not too bad. Okay. That's all the announcements I know of. Do you have any questions? Anything we've covered so far? Okay. So I just was doing Theorem 211, which is on page 70, and this is basically what it says. Now, what we're talking about now are systems of equations. Remember, we were doing those much earlier, okay, where you have your coefficient matrix, and you augment that with the solution matrix, or vector, and then you do row reduction on it. That's how we used to do it. Here's another way to do it. In this way, you can tell whether you've got a solution or not. If that coefficient matrix, of course, now to work, this has to be squared. In other words, the system has to be squared. Same number of equations as you have variables. If you don't have that, it's not going to work. Okay. So if that is a square coefficient matrix, and that's an invertible coefficient matrix, then you can basically write down your answer. The solution matrix, the variable matrix x, or vector x, will be the inverse of A times the solution matrix of vector B. It's that simple. Now, what's not simple about it is getting the inverse. We saw that last time. You have lots of possibilities for pitfalls there. But if you can get that inverse, and guess what? With computers, or even with graphing calculators, there is a way to get inverse matrices. Okay, it's not super easy or quick, but they do it. You know, and if you're careful doing the input, it'll do the output for you. Okay, so they have a little proof here. Let's just do it quickly. Okay. Now, what's given is A is an invertible matrix. And you're starting with A times the vector x, that's the variable vector, x1, x2, x3, x4, whatever, equal to your solution matrix, 7, 3, 18, 4, whatever past the equal sign, that thing. Okay? Because A is invertible, that's given here, you can take the inverse of it, right? So we'll do the inverse from that side and the inverse over here from the left. The direction of taking the inverse matters, okay? Now, we know this is the identity matrix. A inverse times A is always the identity. If it's invertible, that's the identity matrix. So that leaves you with just X. And guess what that is? It's A inverse times B, which is exactly this. Now, for some reason, they took several steps to say that. It's basically here in 2. Yeah. So, pretty easy proof. So, let's do example 8. So I'm going to go to a clean page here and erase all the ink off that one. It says use an inverse matrix to solve each system of equation. Now here is the big advantage of using the inverse matrix. Sure, you can do Gauss elimination much quicker than you can do an inverse matrix. You can do Gauss-Jordan elimination a little bit quicker than you can do an inverse matrix. But if you're doing the same inverse matrix for several different solutions, which sometimes happen, if all your inputs are the same and you're looking, well, can we come out with this output, or can we come out with this output, and looking at different scenarios, if your input matrix is the same, once you've done the inverse matrix once, you can use it over and over and over again. Whereas Gauss-Jordan, you have to go through the whole process every time you change that last column. Okay? So that's what this is going to do for us. Use an inverse matrix to solve each system. I'm going to write down the first system, and this will be 2x plus 3y plus z is equal to -1. 3x plus 3y plus z is equal to 1. And 2x plus 4y plus z is equal to -2. All right. Now it says use an inverse matrix. Now I can almost hear you now saying, oh, but it'd be so much easier if we did Gauss-Jordan elimination. And yes, it would. A little bit easier. But let's do what they say. Now, here's what I want to do. This is not how they're going to suggest doing it, and there is a reason for it. But what I would want to do, you see, obviously you don't have a leading one anywhere here, right? And that's what you want to have first. So you could divide this equation by 2 everywhere, or what you do your matrix do that. That will give you 3 halves here, 1 half here, and a 1 half here. So you have some fractions in it, -1 half. You can divide this one by 3, and you'd have 1, 1, 1/3, 1/3. Okay, not 3 fractions, but 2. Okay, or you can divide this by 2, and you'd have a 1, 2, 1 half, and -1. That's what I would want to do. Now here's why. Well, 1 is fewer fractions, but number 2 is 1 half is, you can write as a decimal just as easily. 1/3 you can't. That's what, remember last time when he was rounding off, that propagated some errors for you. So if you could use a terminal decimal or a fraction, that does it for you. So that's what I would want to do. And therefore, in doing that, I would want to rearrange this even before I began. Because it doesn't matter what order you do. That's not what the book's going to do. It's going to take this matrix and then start rearranging. And it's still going to work well. But you see, it's going to keep these in the order they originally were. And we got to come back and use those. So it's whether you rearrange now and then remember to rearrange these, or do the matrix and then do the rearranging, and then you'll be okay. Which way you want to do it?
Rearrange now.
Rearrange now. I like that idea. But remember, we're going to have to do the next 2 the same way then. So I'm going to rearrange the matrix. And I'm going to put this row first. Okay? So that's going to be, and I'm going to divide by 2. 1, 2, I'm going to put 0.5. Okay? And then -1. Oh, wait, no. Remember, we're not doing the other. We're just doing the inverse matrix. And why did I draw that? Because to do the inverse matrix, we have to adjoin the what?
The 0?
The identity matrix. Yeah. Which would be now, since we're changing everything, I'm going to go and do this to be 1, 0, 0. Okay? Now what we could do is Since this was the last row, and it's real easy to do, just do our 0, 0, 1 there. Which way you want to do it?
We can do the 0, 0, 1.
Do it? Okay. So that would have been our first step, the way I was going to recommend. So let's make, well, it didn't erase, did it? Okay. That still didn't erase. There we go. Okay. So we'll make that 0, 0, 1. Now we won't have to remember 0, 0, 1. Okay? Now all right, well then what we'll do now is just swap these two rows. No, we can do it the other way. Okay, let's do it this. This will now be a 2, 3, 1, and then we'll put, this would have been the 1, 0, 0. Okay? Okay. Because we're just moving things around. So that would have been a 1, 0, 0. See, that's the one on top. So we're going to do that. Okay? And then the next is a 3, 3, 1. And that was our middle row, so that's a 0, 1, 0. This pen is so slow right now. Okay. All right. That's going to be the matrix we try to read. I've already done the first step. Actually, the first two steps. Move rows around and also divide what wound up being the top row, it was the third row, by 2. Okay, what do we do next? We want this to be a 0. So it's going to be a -2, row 1 plus row 2. Okay? So, we're using our row 1 so it stays just like it is. 1, 2. Do you prefer 0.5 or 1/2? I don't care. Okay, let's do the 0.5. 0, 0, 0, 1. Okay. And then let's do that to the second row. -2 times row 1. -2 plus 2. 0. -4 plus 3. -1. This will be a -2 times a half, or 0.5 is a -1 plus 1 is a 0. A -2 times 0 is 0 plus 1 is 1. -2 times 0 plus 0 is 0. And -2 times 1 is -2 plus 0 is -2. Okay. Done. Okay. Now, third row, what will we do? Second?
Subtract by 3.
Yeah, -3 times row 1 plus row 3. Okay? Now, that will be 0. Isn't that -1 again?
Yes.
Okay, -1. And then -3 times 0.5, unfortunately, is -1.5 plus 1 is -0.5. Okay? This drives me nuts, okay? And -3 times 0 is 0 plus 0 is 0. I can do that one. -3 times 0 is 0 plus 1 is 1. -3 times 1 is -3 plus 0 is -3. All right. Now, I like what we have in row 2. I'm glad we don't have the fraction there. It won't hurt anything, but I like that. What I don't like about it is what?
That row 3.
2.
Row 2.
What don't I like about it?
It's a negative.
Negative at first. It needs to be a plus. And that's real easy to fix. Make that a plus, that a minus, and that a plus. Done. Okay? Now we can start operating on the other ones. What do we need to do to row 1 using row 2 to get that to be a 0?
Subtract.
Okay, -2 times row 2 plus row 1, right? Okay, so negative 2 times 0 is 0, plus 1 is 1. Thank goodness that didn't change. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 0 plus 0.5 is 0.5. Negative 2 times negative 1 is plus 2 plus 0 is 2. Negative 2 times 0 is 0 plus 0 is 0. And negative 2 times plus 2 is minus 4 plus 1 is minus 3. Right? We're using row 2, so that's 0, 1, 0, minus 1, 0, minus, no, plus 2. That's a plus 2. Okay? Now, what do we need to do to get a 0 in the second entry in 3? Add row 2 and row 3. Row 2 plus row 3. That'll do it. 0 plus 0 is 0. Minus 1 plus 1 is 0. Or plus 1 minus 1. 0 times a minus 5 is negative. Not times. Plus negative 5 is 0.5. Negative 0.5. Negative 1 plus 0 is negative 1. 0 plus 1 is 1. And plus 2 times negative 3 is negative 1. Right?
Yes.
And one last thing. Not one. Two last things.
Should it be point yet?
Yeah, it needs to be a 1. How do you make that a 1?
Could you divide by 0.5?
You can divide by negative 0.5, which actually an easier way to do it. And this is where, if that had been a negative 1/2, what would you have said?
Oh, just one, just divide by 1 over 2.
Okay, yeah, dividing by that, which is saying is multiply by negative 2.
Yeah.
Right? Well, negative 2 times the negative 1/2 is a positive 1. And that's real easy to multiply by. Then dividing by the decimal, a little hard. Multiplying by 2, negative 2, that's pretty easy. So we'll do that next. I guess I'll take up the room to do it. Okay, so we have a 1. Well, I'm going to leave that one alone. 0, 1, 0, minus 1, 0, 2. I hope I did that right. Okay, and this one will be a 0, 0. Now multiplying by minus 2, that will be a 1. That by minus 2 will be a 2. That by minus 2 is a minus 2. And that by minus 2 is a 2. Right? All right. Now let's take that row and combine with this. So what will we need to do to get this right here to be a 0? Actually, looking at this, let's just add those two rows together, right? Yeah. Not using this one, using that one. So adding row 1 plus row 3. Okay? So this will be a 1. That would be a 0. Plus 0.5 minus 0.5, 0. 2 minus 1 is 1. 0 plus 1 is 1. And minus 3 minus 1 is minus 4. So there is what I hope is A inverse. Goodness gracious, it's pain in the neck. I hope that's A inverse. Before we go any further, let's make sure it is. Yuck, I messed up something again. It's supposed to be a minus 1, 1, 0. Oh, wait. Now, what I'm wondering is, because I rearranged, is that why it's different? I thought I took care of that. Let's see if we started at the right place. Well, I didn't. I started differently. 2, 3, 1, 3, 3, 1, and 2, 4, 1. That's where I started. And I acted like I was augmenting that with the identity matrix. Then I rearranged the order. So I think I did all that right. but we must have made a dumb mistake somewhere. I don't know if it's worthwhile trying to find it or not. Ah, I think I see it right off the top. Yeah, this was a -2 here, and somehow I left off the minus sign there. No, we're not using that -2 yet. Sorry about that. Wait. That should have been a 1. Okay, sorry. Okay. Let me make sure the other two are the same. Yeah. Okay. So let's see, we multiplied that by -2 and added to that. So it gave us a 0, a -1, a 0, now how did I get, that should have been a 1. Oh no, I went back and changed that. Okay, that's fine. A 0 and a -2. Yeah, that was right. And then the next row was a multiply -3 times that. That would be a 0. Ah, that's where it was. -3 times 2 is -6 plus 3. That would be a -3 here. All right. That's where the error occurred, and that's going to change everything else. So rather than going back and doing all that, I'm going to use theirs, okay? And this is what they claim it turned out being, which I can believe now. So I'm going to erase everything, including my error, okay, now that we found where it was, okay. Let's go on and erase that. That first step was okay, but I'm going to erase this. Well, it's not erasing. Oh, there it goes. Okay. Okay. Just so people won't look at it later and say, wait, I can't understand how they get from here to there. Made a dumb mistake. Okay.
You'll have to go back and edit it on the video.
No way. Okay. All right. And let me just write what A inverse is here, rather than going back. But that one error, I think, is what carried through. So this inverse is -1, 1, 0. -1, 1, 0. -1, 0, 1. And 2, 4, 0. No, 2, 4, 1. No, I can't read. I was looking at the wrong thing. This part may be part of my mistakes. Yuck! Okay. Let me go back and check, because I have to put the book over here. You know, I'm left-handed. I'd rather have the book over here, but I don't have room here because the cord is too short. You know, I have to be here. So let me get this again. Let me check it again. -1, 1, 0, -1, 0, 1, 6 minus 2 minus 3. Six minus 2 minus 3. All right. Finally got it right. Okay. Now, so what do we do with that? There's your A inverse. We take this A inverse. Well, I'm going to do it down there in a minute, but let's do it here. And I'm going to first multiply that by this vector here. -1, 1, -2. So you see, all the work was getting the inverse, and that's where the errors came up. But once you get the inverse, then it's just a simple multiplication. Well, can you multiply those two? Here's Daniel. Double the class size. Okay. Okay. Well, what size is this one? 3 by 3, and this one's a 3 by 1. So sure enough, these two are the same. It'll give you an answer. That's a 3 by 1. That's exactly what we want. So let's see what we get. A 3 by 1. So that first entry is going to be, that's the 1, 1 entry, first row by first column. So that would be a, again, 1.
Oh, 1.
1 plus 1 is 2 plus 0. So that first entry is a 2. See where that came from? Okay. Yeah. You're doing, the second one is going to be second row by first column. That's a 2, 1 entry, right? So that would be a 1. 0 plus 0 is 1. Minus 2. 1 minus 2 is negative 1. Okay. So the next one's a negative 1. So to get the answer is real simple. Just getting the inverse, that was not simple. Okay? But it wasn't terrible. Okay? The next one will be negative 6. Okay, this is a negative 2. So negative 6 minus 2 is negative 8. Plus 6. So negative 8 plus 6 is negative 2. Okay? So that tells us that first system of equations that we had here, the solution is 2, negative 1, negative 2. Let's see if that works. Okay? 2 times 2 is 4. Minus 3 times 1 is 3 times 1 is 3. So 4 minus 3 is 1. And then minus 2 is minus 1. That works. Let's do this one. 3 times 2 is 6. Minus 3. That would be 3. Minus 2. 3 minus 2 is 1. Yes. Let's do the last one. 2 times 2 is 4. Minus 4 is 0. Minus 2 is minus 2. Yeah, it worked. Okay. The second system of equations we're going to try to do is this one. 2x plus 3y. My pen's not writing. Such a pain. Plus z is equal to 4. 3x plus 3y plus z is equal to 1. And 2, oh no, it's not. It's 8. The pen has gotten incredibly slow. Okay, 8. Okay, and the third one is 2x plus 4y plus z is equal to 5. Okay. Now, how would you proceed with this one? You do your coefficient matrix again, and then do a row reduction. Please say no. Because guess what? The coefficient matrix of this one is identically the same as that, and you've already done the inverse. You just use the inverse. So we already know that's the inverse, so we'll do A inverse, which is minus 1, 1, 0, negative 1, 0, 1, 6, negative 2, negative 3, and then multiply that by this 4, 8, you got it. And we see what we get. That's going to be a 3 by 1, right? Okay. So let's do the math. And what do you get? -4 plus 8. No, you multiply. -4 plus 8 is +4 plus 0. That would just be 4. Next. -4 plus 0 plus 5. -4 plus 5 is 1. Next. 24 minus 16. 24 minus 16. Oh my goodness, what is that? 8? Yeah. 8. And then we have minus 15. That would be a -7, I think. Okay? Yep. 4, 1, -7. You could go back and run the numbers through, see what you get. I think you get the same answer. Okay. All right. Sorry. My nose is itching. We must be going to have company. Okay? Now what we're doing here, for those who just came in, we have a new way to solve systems of equations. As long as you have same square system, meaning the same number of equations as you do variables, not columns, variables, okay? That's called the square system, okay? And if that square system, you pull out the coefficient matrix alone, not the coefficient matrix with the augmented solution vector, just the coefficient matrix. If that coefficient matrix is invertible, it's square, we guaranteed that, so if it is invertible, then you take the inverse of it. And that's what we did before y'all came in, and I made some dumb mistakes. We didn't get the right answer, but this is the right answer. If you listen, you'll see where those dumb mistakes showed up. But anyway, that was the inverse for that coefficient matrix. But notice here, this is a different system of equation, but with the same coefficient matrix. So even though finding the inverse is longer than doing Gauss-Jordan elimination, or even certainly Gauss elimination, it's still, if you have to do it more than once for the same matrix, it's easier than doing the other two. Because these, you can't just go through and change. You have to do the whole matrix again. So the third one that we're going to try to attempt is 2x plus 3y plus z is equal to 0. 3x plus 3y plus z is equal to 0. And 2x plus 4y plus z is equal to 0. That's a homogeneous system. All of those are equal to 0. Okay? Anyone want to make a guess what this A inverse, that's -1, 1, 0, -1, 0, 1, 6, -2, -3, goodness, that's an ugly 3, times 0, 0, 0 gives you? Anyone want to hazard a guess? Didn't leave enough room over there, but that would be a 3 by 1, right? What do you get when you do this? -1 times 0. Oh my goodness. Spirited and truth. Okay? Muhammad is here. All right. We actually have the majority of the class here. First time in a long time. Last time we had 3 out of 7. The time before that we had 2 out of 7. The time before that we had 3 out of 7. So it's been 2 weeks ago. That Thursday we had 5 out of 7. Okay. Now we got 4, which is better than before. Okay. But what does that give us? There's a 0. So our solution is x equals 0, y equals 0, z equals 0. Of course we know that's true, because if this is, we know this is an invertible matrix, and it has a unique solution then, and since these are all 0, the only way you can get this to be 0 every time is for every one of those variables to be 0. Okay? And sure enough it is. That's your one and only solution. 0, 0, 0. I didn't have room to write it, but that's what it is. So you see how if you are using the same coefficient matrix repeatedly, do the inverse once, and then use this technique. If you're only doing a given system of equations, go on and do Gauss or Gauss-Jordan. There's no reason to do the inverse matrix unless you're going to be repeating that with different solution vectors. If you have them, then do it. All right, that does finish 2.3. Homework exercises here would include any of the odds 1 through 5. They're all at Calc Chat and in the back of the book, by the way, too. Any of the odds 7 through 29. Now, those last couple are a little more involved, but you can try them if you want to. Any of the odds 31 to 35. Either 37 or 39. They're all answers are at Calc Chat of the odd numbers. Either 41 or 43. Either 45 or 47. Either 49 or 51, or both if you choose. 53, 55, 57, 59. 61. Goodness gracious, my hand's hurt. Okay. Oh, there's 61. Okay. Talking about a flexibility matrix, and then the inverse of that is the stiffness matrix. We talked about that briefly in the book, I think. Or no, maybe it was here. I assigned these before. All right. Then true-false is 63. 65 is a proof. 67 is a guided proof. 69 is a proof. 71 is a proof. 73 is a writing exercise. You can choose to do that if you wanted to. 73. 75 is, you could do 75. That's should be at Calc Chat. 77 is another proof. Now, this is an unusual name. This is called the householder matrix. And for the life of me, I do not know where that comes from. Then 79 is another. 81 is a writing exercise, and 83 is a writing exercise. So you can choose whether you do those or not. They're completely up to you. All right. Goodness gracious. I hope I don't feel this bad tomorrow when I'm driving 8 to 10 hours. That will be one miserable trip, or two miserable trips, actually. All right, let's do 2.4, elementary matrices. Now, if this seems like you've seen it before, you have. Not in these terms, but you've seen these 3 steps before. It's basically a definition, okay? There are 3 elementary row operations. We did them once with equations, we did them again with matrices, and we're doing them again repeated here. The 3 allowable elementary row operations are these. 1, interchange any 2 rows. Okay, we did it in that last example that we started. Most of you weren't here. Terrell was the only one that was here at that time. We interchanged actually 3 rows, okay. Number 2, multiply a row by a non-zero constant. And we did that too, I believe too. Yes, we did. Multiply a row by a non-zero constant. Okay? And the third one, the one we do most of the time, add a multiple of one row to another row. Okay, those are our 3 elementary row operations. Get used to them. You've seen them 3 different times, at least 3 different times now. Ought to know them by now. Now, in this section, you'll see how to use these matrix multiplication to perform these operations. First, this order is sort of a little bizarre here. Here's a definition of an elementary matrix. First, it's going to be square. Okay? It's got to be square. An n by n matrix is called an elementary matrix okay, when it can be obtained from an identity matrix, bless you, okay, from an identity matrix, IN, of course that's got to be in size n also, by a single elementary row operation. I'm going to shorten this to ERO, elementary row operation, by an elementary row, a single elementary row operation. Okay? Now, the next example, I hope is pretty easy for you. It's just going to be identified. Are they or are they not elementary matrices? Okay? Here's the first one. 1, 0, 0, 0, 3, 0, and 0, 0, 1. Is that an elementary matrix? Yes, you got it by multiplying an identity matrix, row 3 by 3, row 2 by 3, because that's all you did. A single elementary row operation multiplying one row by a constant. We did it. We multiplied the second row by 3. Done. That's an elementary matrix. Okay? How about this one? 1, 0, 0, 0, 1, 0. Okay, is that an elementary matrix?
Yes.
Second?
Yes.
Yes, why? Okay. Now, 2 things wrong with that. Okay. The first thing is an elementary matrix has to be square. Cannot be rectangular. So that's the first thing. The second one, you said multiply the third row by 0. What could you multiply? Look at number 2. Multiply a row by a non-zero number, constant. Okay. Can't ever and don't ever multiply anything by 0. Ever. Because you lose all the meaning. It becomes 0 automatically, and then, yeah, you lost all meaning. So that's not an elementary matrix because it's not square. And you can't multiply, or elementary row operation is never multiplying something by 0. Okay, how about number C? That's yes in Spanish. 1, 0, 0, 0, 1, 0, 0, 0, 0. Is that an elementary matrix? Second? Why? It is square, that's for sure, but not all square matrices are elementary matrices. What did you do to the identity matrix to get that to be that? Say that one more time. Okay.
Would it be the last zero at the bottom?
Okay. Multiply the last row by 0? We can't do that. We just said that.
Not by 0, but should it go diagonal 1, 1, 1? It should be 0, 0, 1 for the last one. That's why.
Yeah, you do a single elementary row operation. Okay? Swapping 2 rows is not going to do it. Okay? Multiplying by a non-zero constant is not going to do it. And adding a multiple of one row to another row is not going to do it. This is not an elementary matrix. That's a no there too. So this was a yes, no, no. Okay. How about D? This is 1, 0, 0. Pretty exciting stuff, huh? 0, 0, 1 and 0, 1, 0. Is that an elementary matrix? Why? Yes, we just swapped the second and the third row. That's all we did, and that is a single elementary row operation, so that's a yes. Okay? Number E. 1, 0, 2, 1. Is that an elementary matrix? Why not?
Because if you multiply second row by 2, then 0, 1 will be 2, 0, 2 instead of 2, 1. So it's not. Because there will be multiple operations to get to 2, 1.
Okay, say that one more time.
The second row cannot be just, we cannot get to the second row with just one operation. We have to do multiple operations to get to 2.
What multiple operation did you have to do?
Because if you do if you multiply the second row by 2, that will give you 2, 1. I mean 2, 2. Actually 0, 2, not 2.
Any other ideas? This is an elementary matrix. Multiply the top row by 2, add it to the second. Remember, that's one. Adding a multiple of one row to another row. Twice the top row. You go back to this is 2 by 2, so there's your 2 by 2 identity matrix, right? Do 2 times this, add it to that. Single row operation. So that is an elementary matrix. Okay? Now, F. 1, 0, 0. 0, 2, 0, and 0, 0, negative 1. Is that an elementary matrix? No, why not? It's what? Okay. I think you're heading in the right direction. You had to do 2 elementary row operations to get this. You had to multiply the second row, not quite that, but the second row by 2, but you also had to multiply the third row by -1. That's 2 elementary row operations. You're only allowed 1. So if that was a +1, yes. If that was a 1, yes. But with both of those being different, no, it's not. So I think you're right on top of that. Okay? So we have a yes, no, no, yes, yes, no. Oh, I forgot to put the no in. Okay, good deal. All right, let's do example 2. All right, somewhere here I have my watch. Oh my goodness. Is it 12:45? Huh?
44.
Okay. But that means we only have 1 minute. Okay, we're not going to have time to do example 2. Okay, sorry about that. We'll start example 2 next time. We didn't do much. Didn't get too far in 2-4, but we did do enough to do any of the odds 1 through 7. Okay, so you can do any of the odds 1 through 7, in addition to the ones from the previous one. Okay, sorry, I don't have any time to spare today because I've got to go over and see if I can get the books for the vehicle because I've got to drive to Mobile tomorrow. Were there any questions? What's that? No, Mobile. Yeah, 4 to 5 hours. Okay.
Well, you said something about 10 hours there and back.
It's, between 8 and 10 hours there and back, right?
I thought you mean like 10 hours to go there.
No.
I was about to say that was a long.
No. It's 4 to 5 to get there, 3 to 3.5 hour meeting, and then 4 to 5 hours to get back. Not a very good use of